Alright, in this video I'm talking about integration by completing the square, which I believe is going to be our last technique of integration. So, before we start, let's look at the AP Calculus course description. So I'm over here, I'm on Big Idea 3, Integrals and the Fundamental Theorem of Calculus. Okay, we're going to scroll down. This is just basically the idea of that integral is the limit of the Riemann sum. There's properties and stuff. I'm actually looking for techniques of integration. And let me zoom in here real quick. Yeah. So, okay, we can use a left Riemann sum, a right Riemann sum, a midpoint Riemann sum, a trapezoid Riemann sum. We know this. Sometimes we can use geometry to evaluate integrals. We know this. Okay, we've done all this. Properties of the integral. Really, all of the things that are in white we've done because we've done all the things in the AB curriculum. Okay. We can extend the definition of the definite integral to functions with removable or jump discontinuities. We know that. We can do improper integrals. We did that last time. And look at that. We have to be determining improper integrals using the limit of definite integrals. Okay. So here we go. We can cook up antiderivatives using an integral, stuff like that. Where is it? Where are the techniques? Oh, yes. Techniques for finding antiderivatives include algebraic manipulations. Okay, that's like factor and cancel. Dividing through by, and you have like x squared plus x plus 1 divided by the square root of x. You could, multiply through by x to the 1/2 power. Those algebraic manipulations, we've seen those, we have experience. Long division and synthetic division, that's when we see bigger on top. Okay, we're familiar with that as well. Completing the square, that's what I'm going to show you today. Substitution of variables. Substitution of variables, when they say that, they mean u du. Integration by parts, that's u dv. And non-repeating linear partial fractions. We've done all of that, except for complete the square. What does that even mean? Well, that's what we're going to find out right now. And then the rest of it is kind of, just other stuff involving the integral that we've already done. So, going over here, let's integrate by completing the square. All right, so I'm just going to start with this integral. What is the antiderivative of 1 over 1 plus u squared with respect to u? Arctangent of u, yes. Okay, so that's equal to arctangent of u plus c. Okay, but we're used to now seeing that u could be some sort of expression involving x. Well, what if u was x minus 1 or something like that? Then I'll kind of carry that forward. But before that, I'm going to remind you of another one. Okay, what about the antiderivative of 1 over the square root of 1 minus u squared with respect to u? What is that one? Arc sine. And if I change that to negative 1 over the square root of 1 minus u squared, that would be arc cosine. Okay, so this is equal to arc sine of u plus c. Okay. Now, I'm going to just kind of go in the arctangent direction, but I'll do a couple of examples after this of, all of the different types that we could run into. So, I'll just say, what if u equals x, how about something more exciting like, x plus 6. Okay, then, 1 plus u squared, well, u squared would be, well, we'd have to square x plus 6, and that's not x squared plus 36. I know y'all know that, but I'm just reminding you. That's x squared plus 12x plus 36. So, if we ran into something like the antiderivative of 1 over x squared plus 12x plus 37, that's going to be something that we can anti-differentiate now. And this is kind of tricky to recognize. It's something that I'll remind you of like the day before the AP exam just in case it shows up. Now, to the best of my knowledge, it has not been something that we've seen on the multiple choice on the operational form the past couple of years, since that got explicitly added to the course description. Okay. And then, you could see if you were just off by 1 in a square root in the denominator of a fraction, that might be an arc sine or arc cosine derivative. All right, so for example, I've got an antiderivative of 1 over x squared minus 14x plus 50 dx. And now what I'll tell you is one of the things that you might be able to figure out that it's complete the square as opposed to, partial fractions or some other technique of integration is if you see the denominator of the fraction is not factorable, but it's degree 2, right? Because if it's degree 2, we're not going to have a way to anti-differentiate it. And it's not factorable, it means it's not going to be something we're going to decompose with partial fractions. So I'm thinking maybe this is an integral that involves arctangent. So I'm going to say, well, yes, x squared minus 14x plus 49 is a perfect square. So what I'm going to do is I'm going to rewrite this 1 over x squared plus minus 14x, whoops, plus 49 plus 1. And then I can rewrite that thing in blue as the integral of 1 over, okay, so 1 plus, this is x minus 7 squared. So if I see the integral of 1 over 1 plus u squared du, okay, then I know it's arctangent of u. So I'll say that the antiderivative of this thing is arctangent of x minus 7 plus c. Okay. Realistically, I'm pretty sure that if we see this on the AP exam, this is what it's going to look like. I feel pretty confident about that. But there is a chance that we could have something involving arcsine or arccosine. All right, and then the next one I've got is one, oh, I forgot my dx. It's one that's got a square root in the denominator and an x squared. Okay, this should be a giveaway that it's going for arcsine specifically because it's positive 1 in the numerator. Also, this is problem number 5 from the Choose the Appropriate Method of Antidifferentiation worksheet, which I will link and the key to that in the description. So what this is this is just off from a perfect square, right? Okay, I see an x squared, a 6x, so I would probably need a 9, but I have 8. Okay, so what I need to do is I need to turn this into, something that looks like an arcsine antiderivative. Okay, so I'm over here. Let's see. Well, this is like negative x squared plus 6x minus 9 plus 1. But this is going to be at least the negative of a perfect square. So I'm going to try that because I'm going for the 1 over the square root of 1 minus u squared. Let's just go ahead and try to do that. Let's make this, let's factor this into, I'm going to actually just work with the thing in highlighter right now. So this is the negative of x squared minus 6x plus 9. Now this is good because x squared minus 6x plus 9 is a perfect square. So that's the negative of x minus 3 squared. So now this integral is becoming, bless you, 1 over the square root of 1 minus x minus 3 squared, which is going to end up being arcsine of x minus 3 plus c. Okay, so these, you've got to recognize them as a complete the square integral, and if you do, then you're going to, complete the square. There are other complete the square type integrals that involve a trig substitution, but those are a little beyond the scope of Calculus BC, so I'm not going to include these in this video. Maybe a little later on I'll come back with a separate video on trig substitution. And that's kind of a topic or a technique of integration that is really good. It's included in most College Cal 1 courses, but it's not on the AP course description, so we're not really going to have time to do it before the exam.